And hello, everyone. I'm Pedro Salas. I'm a postdoc here at the observatory. This June, it will be 2 years since I started working here. It's been a real pleasure. And as Karen and Will have mentioned before, if you have the opportunity to visit, please do. It's an amazing place. If you like radio telescopes, this is, I would say, like Disneyland. The number of radio telescopes is amazing, and you really get to learn a lot about the history and what the future of radio astronomy uh, will look like. Um, Today, I will talk to you about spectral line data reduction. Let me know if you can see my screen. Suppose you can. And also um, hide the video. So I cannot see you and I cannot see the chat. So if you have any questions during the talk, please stop me, just interrupt me. The idea, we're here so that you can make the most out of your GBT observations. And so if you have any questions, please do ask. A bit of background. Um, I'm when I do science, I usually do low frequency spectral line observations. So I apologize if the talk is a bit biased towards that. I also try to cover some of the high frequency specifics, but um, if yeah, if something that is not covered here, just ask, or when you're preparing your observations or reducing your data, please do contact your project friend. We're here to help, and we want to make the most out of the GBT, which is this beautiful instrument you see here on the background. All right, so as a quick outline of what I will be talking about today, I'll give a brief introduction to single dish calibration. I see from the answers you provided when you registered, I see that some of you do have experience with single dish data, some of you don't. So I'll just start from uh, I'll try to start from common ground so that we can all move forward together. Then I will delve into two types of observations: tracking observations, where you're just observing one source, one position in the sky, and you're following it as it moves in the celestial sphere, and how you process this data using GBTIDL, which Larry already briefly introduced. And then we'll jump into mapping observations. That's when you're basically scanning a larger area because you're interested, for example, in the spatial distribution of the emission or something like that, and how we can reduce this data, both using GBTIDL and this other thing that Larry also mentioned, the GBT pipeline. And then we'll go into a bit of details for high frequency calibration, which is the basics are the same, but then the implementation is slightly different just because of the way things have developed. So to start, what is the single dish measuring, right? When we're pointing at a source in the sky, what the backend is basically recording, the backend is something like Vegas, which is just saving the, the power recorded by the telescope. What we're seeing is basically proportional to the temperature of the source we're interested in, and all the contributions to this to the temperature of the system, either from the atmosphere, from spillover, if there are standing waves, or the receiver itself has a finite temperature, which will also generate electronic noise. All those things contribute to what the telescope is recording, and what we get basically what you're observing is power. And what we really would like to know, it's what's the temperature of the source, right? So we are basically measuring this P over here, and we want to go to this temperature here. I'm also using this superscript cal in square brackets because, as we will see, a telescope like the GBT is constantly flicking on and off a noise diode, which then lets us basically invert this equation because there is this quantity known as the calibrator temperature, which is known, and we will see how that works in a bit. Um, So that's the basic idea. We are measuring the power and we want to go to the source temperature. And just as a small note, since the GBT has an unblocked aperture, things like, for example, contribution from standing waves are really small, so that this makes it a really great instrument to go deep and measure spectral lines. If you're interested in more information about and more details about how the calibration works for single dishes, I encourage you to check out these two references as well. So how do we go from this power to the source temperature? Well, what we usually do is measure two things. We will measure the source we're interested in and something we will call a reference or off position. And then if we take the equation from the previous slide and take the difference between the power on the source minus the power of the source and divide by the power of the source, this will be proportional to the source temperature. And well, almost we will get this relation here. So this is the basic equation we have to solve to go from power to temperature. In the process, we'll also need to know the system temperature, which was the contribution from all these terms, including the noise diode. And we can determine this system temperature from observations of the off or reference position or of or reference frequency using this relation down here. So this is the basic math. It's just inverting these equations. Oh, I forgot to mention that. Yeah, this is an approximation, assuming that the response of the system is linear. For most cases, that is true. So these equations hold, and this is what most of the data reduction software will be doing when you're calibrating your data. So moving on, I mentioned that we're going to measure on the source and off the source or at a reference frequency. So there are two methods for doing this, as Dave mentioned in his talk. One of the techniques or strategies you can use to measure on the source and off the source, it's actually just moving the telescope or moving the beam of the telescope in what's known as position switching, where people usually talk about on-off observations. You can also just move the beam by moving the superflector, and you can do it basically away from the beam itself or within the beam itself if your source is small enough. And another way in which we can do this is using frequency switching. So instead of moving the telescope or the beam, what you do is just shift the frequency of your observations, so that then you have basically almost the same contribution from the system temperature, but slightly shifted, and then you subtract these two things. And by shifting, you make sure that your line of interest doesn't subtract itself, because in one state the line is going to be here, and in the other state the line is going to be moved a little. So then when you take the difference, you don't subtract the line from itself. You can use different combinations of these things. For example, you could do on and off observations with frequency switching. The specifics of this will depend a lot on the source properties and your source goals. So again, if you're interested in using these things and you're not very clear on what's the best way, contact your project friend. So now we're going to go into a bit more detail about what these two basic observing methods are. The first, position switching, and the most basic way we do this is just moving the telescope. And as you can guess, well, it's you will lose some of the observing time because you have to slew between the on and off positions, and you will be also spending time on the off position. But using this technique has its advantages over not moving the telescope. As I mentioned before, when we are looking at the source, that's what we call the on position, and this is what the power will look like. So you have the contribution from the source plus the system temperature, and we usually try to pick an off region where there's either no continuum emission or no line emission, so that the power we measure it's basically only the system temperature. In practice, there's always something on the sky, but just have to make sure that we know what there is there, so we don't subtract signal from our line of interest or from continuum. And if you're using Astrid, this is as simple as issuing an on-off command where you tell the telescope um, where you want to go for the off position and for how long. And if you're using a multi-beam receiver, which beam to use. In terms of position switching, well, like I mentioned, the off region should not have emission or absorption if you're looking at lines. And if you're moving the whole thing, particularly at low frequencies, you do want the beam to be at least one beam away from the on position for the off position, so you're not subtracting the same thing from your source. The cycling of this, how often you should be switching between on and off, will depend on the frequency at which you're observing and how broad the features are. Usually for spectral lines, every few minutes or so, it's good enough. And this method is good for observations of broad spectral lines, especially if you have an off region where you don't have any emission, any spectral line emission, or sources where you have a lot of spectral lines, and maybe using frequency switching is not going to work just because the spectrum looks like a forest of emission and absorption lines. And like I mentioned before, some of the drawbacks of using this method is that you lose some time going back and forth. And as with any method we use for calibrating our data, it's only going to be as good as the assumptions. So if the on and the off positions, for example, have very different continuum levels, that might affect the the shape of your baseline, so where you have no spectral line emission, and you might end with some residuals there that you will need to correct for after. The other method is frequency switching, where, as shown up here, you're basically switching the frequency of the local oscillator so that the line of interest appears at a different channel each time. And then you can take the difference between these two things, and that will remove most of the system temperature after the local oscillator, and give you a more or less flat frequency response, except in the regions where you had the line on and the line off. You will end up with something where you have your line. If the line is in emission, it will be in emission in the end result, and in absorption where you took the subtraction. Some of the comments about this, the off region, so where you're moving your spectra and how much you're shifting it, should be such that there is no emission where you're using as reference. So, for example, if you have too many lines together, you might move the line you're interested in, but another line might come on top of it. So you would subtract that while doing the referencing. And it's also very important to be aware of the RFI conditions. So you don't want to switch the frequency so that you bring RFI into the band. This is useful for observations of narrow spectral lines in general, particularly in regions where you don't have a lot of spectral lines, so you don't have problems of crowding. And some of the drawbacks is that, well, you need to know where your line is, so you know how much to shift, and you need to know a bit about the spectrum, so you don't end up subtracting other lines from your target. Depending on how much you shift the frequency, the response of the system is going to change. So you're going to end up with residual baselines if you use a very large shift. And since you're subtracting the same thing, you're basically looking at the same position and subtracting it from itself, you cannot get continuum measurements using this method. I also talked about this noise diode this calibrator temperature that's in some of your measurements. Well, that's basically if you have the front end of the telescope, and you have this the signal coming in from here, and you got your first stage of amplification. Every other cycle, in general, the the front end will inject this source of noise into your signal, which is known beforehand, or you can rederive the calibration. I mean, rederive its temperature by looking at a source of known flux density. And this will then enable you to convert from power into temperature units, because this way you can measure the system temperature, as we saw in the first slides. So that happens every so often. And a few notes on this calibration temperature, or the temperature of the noise diode. Sorry. By default, GBT, the GBT will fill your SDFITS table with a value for TCAL, but this value might have been derived a long time ago, so that might not really apply for your for the current status of the noise diode. So you have to really, it's really recommended that you take the time to observe a calibrator source, any of the 3C sources cataloged by Perley and Butler, for example, can be a good source. And you have to observe this so you can rederive the temperature of the noise diode. Why? Well, this is an example where the Godi et al. I think this was for H1 manga, for the H1 manga survey, which is a project in which they observe H1 from galaxies, and they have been observing for a couple of years now. They basically compare the temperature of the noise diode as it is in the metadata of their SDFITS files to what they were getting when they observed a source of known flux density, and what they get was that the value is roughly a factor of 1.2 larger than what it's in the metadata. So it's important to apply this correction so you get an accurate temperature scale and an accurate spectral line profiles, and you get the correct amplitude of your lines.
Can I ask a quick question?
Yes, please.
So the noise diode is giving you the short time scale variations, and the calibration is giving you a better overall idea of what the flux conversion should be? Is that how it works?
Basically, you're going to observe a calibrator source to know what the temperature of the noise diode is. So then you can use this information to invert the equations and go from power into temperature. And in general, the temperature of the noise diode is stable over periods of months for most receivers. I think the only one that's really variable is the KFPA. So usually you would do this only once per session, or maybe in longer timescales. Does that answer your question, or?
I think so.
Okay. Yeah. Yeah. So yeah, but the basically, yeah, injecting the noise diode allows you to basically remove this, since you're always injecting the same temperature into the system, and you're doing this basically for each integration. It allows you to remove like short time variations in the system temperature. How to pick a calibrator? Well, you want to know the flux density of the source, so you can know what it should look like with your telescope. Hopefully, it will be stable in time, so you know what, or if you know what its flux density is going to be during the time of your observations, that's also handy. It should be point-like, so it should be smaller than the beam, because you do not want to observe like something that it's complicated to model in terms of how it couples with the telescope beam. And here two references which give you some of the properties of these sources, like how stable they are in time, what are their sizes, and what is their radio spectral energy distribution as a function of frequency. So you can use those to calibrate your data. So that's the basic theory behind the calibration. So you're going to measure power. You're going to do it on your source and either at a reference position or at a reference frequency. Then you're going to take that and convert that power or those counts into a temperature or a flux, whichever works for the science you're trying to do. And the way we normally do this, you don't have to code all these equations yourself and solve them. We usually use this package called GBTIDL, which is the observatory supported data reduction software. It's written in IDL, but as Larry pointed out, it's not exactly the same as IDL. That's why it's GBTIDL. Whenever you log into one of the data reduction machines, you can just type in GBTIDL and do your data reduction. Just bear in mind, don't do it from Prospero because that's just for logging in. Go into one of the data reduction machines. And it's mainly geared towards spectral line data reduction. It's possible to do continuum reduction in using it, but that that's something you would have to discuss in a bit more detail with your project friend, how to actually get that done. And of course, it knows about most of the observing modes that you can use, like position switching, frequency switching, beam nodding, and so on. And in this website, you can find the documentation, the source code, and a sort of like quick guide that walks you through what it can do and how to do it. And I strongly encourage you to go there and check it out, what it can do, in particular the quick guide. So now we're gonna go through some of the commands you can use in GBTIDL. This is by no means an exhaustive list. It's just to give you a taste of the basics. And the first thing you wanna know when you're facing a new software package is how to get help. And there are three ways which I found listed in the GBTIDL quick guide. The first one is just using usage, comma, and then the command name as a string. And this will give you basically just the signature of the method. So basically what arguments you can pass to it. If you want to have more information, then you add the verbose flag. Then it will also tell you what the command is doing and more detailed description of what the different parameters you can pass to it are. And if you really want to look at the source code, you can also use this source option, and then it will really give you all the details and show you what is actually going on behind the scenes. And even though in general one would want to maybe avoid going into a source code, I found particularly while preparing this presentation that it was quite useful to go there just to get a deeper understanding of what's really going on and what are the limitations of different things. So yeah, feel free to use these commands, of course. Once we know how to get help out of GBTIDL, we want to be able to access our data, right? So if you're actively observing and the telescope is recording your data in spectral line mode, of course, you can go into GBTIDL and type online. That will directly connect into the project that's being written at the moment. If your data has been written and it's still in the SDFITS area, so it still hasn't been archived or completely archived, you can use the offline command, comma, and the project name using this syntax where it's basically the semester and the project code and also the session. So each session has its own file and it will connect to this file. And if your data is no longer in the SDFits area, or you have created your own file and you want to be able to keep working on it, you can also use file in, and you can specify the full path to your SDFits file, and it will load it, and you can then continue like you would do normally. Another thing to know about the GBTIDL is that it uses data containers. So these are basically internal array-like variables that you can use, and, and GBTIDL will use these internally. So whenever you, for example, get some data, it will put the results from the operation into one of these data containers. In particularly the first data container, which is known as the primary data container, or PDC. So if you, for example, want to look at the total power of your data, and you get TP command, it will be put into this PDC. So this is an example of how, for example, this is an example of how to get the third row of an SDFits file and save it into variable X. So you would do get rec and the number of the row you're interested in, and that would save the contents of record 3 into the PDC. And then if you want to save this into a variable X to do something else with it, you can do X equals get data, and then the contents of row 3 of your SDFits are going to be in X. And then, for example, for some reason, you know that the first 500 channels of this third integration should be 0. You can set them to 0, doing something like this. You can also do arithmetic operations between containers. So, for example, if you want to add two containers together and save them into a third, you can do add first one, second one, and third one. You can subtract them, divide them, and multiply them. I think you can also do scalar operations on them. So for more details, again, I encourage you to visit the GBTIDL documentation, where you can find more of these commands and how to use them. To get information on your observation, once you have loaded an SDFits file, you can get a summary of the observations using the summary command. And this will basically list all the scans, the sources, the number of spectral windows for each scan, the number of integrations, as well as information such as where the telescope was pointing towards, things like this. If you use the header command, you will get the metadata of the PDC. And if you use the list command, then you will get information for every row in the SDFits. This is usually a lot of information, because one scan can have hundreds of rows. You can also do some data processing in GBTIDL. For example, we can do some baseline feeding using this set of commands here. One thing that I forgot to mention, but is that I will show it in a moment, is that to fully use GBTIDL, it's highly recommended to have a display available. So, because whenever you, for example, retrieve some of the data from using GBTIDL, it will display this data, the spectra, in a graphical user interface, and you can interact with that display and do things like, for example, specify the region where you want to do some baseline fitting, or if you want to fit a Gaussian, you can also specify where to fit the Gaussian, things like this. So it's very important that you have a display available when using GBTIDL. So in this example, for example, once you bring up a spectra and do set region, it will ask you where you want to do the baseline fitting. Then you can set the polynomial order. Then if you do V-shape, it will fit the polynomial. And then when you do baseline, it will actually subtract it. And we will go through this in a real example in a minute. You can also smooth data using a Gaussian kernel if you would like, or a boxcar kernel. I'm not sure if there are more kernels available, but these two are usually good. I think there's probably also a Hanning kernel. can't remember right now. And if you wanted to fit, for example, a Gaussian to your data, you can use the command fit Gauss, and it will show you. It will ask you to specify the regions where you want to fit it and to provide starting guesses. So let's go into GBTIDL and actually do some of these things. So I'm gonna stop sharing here. Are there questions so far? No? Okay.
You mentioned ST fits. What was that?
Oh yes, sorry. Oh yeah, SD fits. It stands for Single Dish Flexible Image Transport System. And are you familiar with FITS images, for example,
No.
FITS cubes? Yes. So SDFITS is
No.
just
No.
another convention on how to store the data. It was created to basically store data from single dish telescopes. And unlike a FITS image, it contains table data, and tools like GBTIDL and the GBT pipeline and the GBT grider know how to interact with these SDFITS files. So in for most cases, I think you don't need to worry too much about what's inside the file, but it's just the observations taken by by a telescope like the GBT. They can be saved into this single dish fits format. It's just a convenient way of transporting the data because it's a, a format with well-defined characteristics and properties. So anyone should be able to write software to operate on SDFITS files based on the description of the files. Okay, share now my screen. Can you see my FastText session? Okay, so I'm gonna assume yes. So the first thing we do, like Larry showed, is, well, we can first list the content. So there's nothing in here except this script, average rcg.pro, which if you're following the slides, you can find its contents. I think it's in the next slide. Let's just show its contents. So all it's gonna do, it's well, let's first go through some. Let's start from the beginning. So we're gonna call GBTIDL, and let me see the prompts, and oh, welcome to GBTIDL. So we're in, and we're gonna work on this dataset kindly provided by Natalie Butterfield and Amber Bonsal, where they did position switch observations of two galaxies from the Redshift survey catalog, I think it is, where they basically observed H1 from these galaxies, and yeah, and they have been Amber and Bren have been working on producing some quick guides based on this data. So we're going to take advantage of this data set. So we go offline, and it will tell us, okay, we could connect to it. If we were to specify something that doesn't exist, we would get an error message, no spectral lane data found. So, but if it says it could connect, then we're good. Then the first thing we might want to do is, okay, just connected to its mystery observation, what's in there? So we can list it using summary. This is how it looks. It tells us the scan, the source that was observed, what was the velocity of the source, and this is set by the information you provide in the catalog files while you're preparing your observations. It tells us which kind of observation was being done. So in this case, it's off-on, so that's the on and off, but flipped, so first off, then on. It will tell us which, for a given procedure or scan type, there will be different sequences. So off-on, you always have an off and an on, so there's always a 1 and a 2 in the sequence number. It will tell us what's the rest frequency of the observations, the number of intermediate frequencies or spectral windows, the number of integrations in each scan, the number of beams for the observation, and the telescope was, where the telescope was looking at in the local azimuth and elevation system. So if you were looking at the Clio window, this would be what the encoders would show. So we have this. Let's see how our data looks like. The most basic, well, not most basic, but one of the ways of just retrieving the raw data, but average in the scan, is using this command get TP, which is short for get total power. So when we do get TP, we're just going to get the P on or P off. We're not going to reference it with anything, and it's just going to show what the power looks like. So we can get TP, and let's try first usage. Sorry, that's not the way you do this. Usage. Sorry about my English. And it will tell us what command, what arguments we can pass to it. So we can tell it, we have to tell it what the scan number is, and then all these options in brackets are optional. So we can tell it, okay, if we had multiple spectral windows, which one we want to look at. By default, it always goes to the first. If we wanted to look at a specific integration, we can also tell it which one, and so on for a lot of lots of other options. If we wanted to know more, of course, we can do verbose, and then it will also tell us more about what each one of these options is. So it's really useful. So let's just get TP for our first integration, which I think it's number 5. Oh, sorry, it's number 6. And this is the user interface that pops up whenever you bring up some of this data. So you can see here that the data is only in counts because this is the total power, and this is the shape of the spectra that comes out. This roll-off here is because of the way the backend Vegas processes the data. So usually you don't want to use the data here at the edges because the signal, the amount of signal you're getting in drops drastically. So you just want to stay within this region of the spectrum. And you can notice here, for example, very close to the frequency of the H1 line, we have some galactic H1 emission. And if you want to zoom in, you can use the middle click on your mouse. You draw a box, and you can see this beautiful H1 galactic H1 spectra, which is almost all over the sky. There are a couple of other things you can unzoom up here. You can see here that the spectral axis is in gigahertz. If you want to change it to velocity, you can click here in this gigahertz up here and go to kilometers per second, and it will change the spectral axis to velocity using the rest frequency provided in the metadata of the observations. Let's do something more interesting. Get position switched. So since these were on and off observations, GBTIDL automatically will know if we tell it to get PS for scan 6. It will automatically know what was the on and what was the off scan, so we can do that. And we go to the plotter again, and we see that now it looks flat because we did the on minus the off, so it removed most of the baseline. You can still see there are some things here along where we have the galactic emission, probably because both the on and the off position have galactic emission, since H1 is everywhere. And we also have now that the temperature is in kelvins. So that's that. And let's try something else. So for example, I was showing this script. Let's see if we can go back to that. Yeah. So well, the first thing I wanted to ask you, if you're trying this yourself, you can type it in the chat. What is the velocity of the line you're seeing? And you can go and compare it with what Barton et al. Derived in 1996, see if it agrees or not. So go ahead, try it, open this data set, change, get the position switch data, show the spectrum, turn it from gigahertz to velocity, and you can type in the chat what's the velocity of the line, roughly, just by looking at it. Are you? Sorry. Yeah, so those are the instructions there. So you can try this and do it on the, type it on the chat. And while you try that out, I'm gonna go and just go over, for example, a GBT, well, an IDL script that would then collect all the scans of a source, or all the scans between a start and an end scan that we tell it. It will average them and then show the result. So to do this, we would do get PS on every one of the scans that contain signal. If we do get PS on the on or on the off reference of the same sequence, it will show the same. So that's not relevant. That's why we loop over each two scans. And the accum command will save this the contents of the primary data container for so that we can later use this average command and average them all together. So if you were to save this average RCG in, sorry. Yeah, so if you were to save this file within your home GBTIDL Pro directory, then you can come back. Sorry about the flipping screens. You can go back and type .r average RSG, and that will basically compile the set of instructions that's within our script, and then we can just use it. IDL doesn't know about lower and uppercase as far as I'm aware, so it doesn't matter if it's upper or lowercase. And you can say, let's do summary again, just to be clear. So we have, for one source, we have scans between 6 and 9 are the same source, so we can do average SG between 6 and 9, and it would just collect scans 7 and 8 and put them all together. And this is how the average looks like. Right, so the signal to noise should be better because we average to Spectral. Now, if we wanted to smooth this, we can use G-smooth by a factor of 15, for example. And we can do show again, and we see that the noise is much better. The scatter around is much less. And for example, if we wanted to do some baseline fitting, I have to remind myself how to do that. Apologies. So we can do set region, and then it will ask us to define where we want to do the baseline fitting. So you just, it tells you down here also how to do it. So that's really convenient if you are not familiar with it. So you just click with the left button to select the region, and then with the right button it stops. And these are the regions that were selected. Once we have the set region, I think it's nfit. Since it looks pretty flat, we just use an order 1 polynomial, and then I think it was B shape, and it would fit, and then baseline, it should remove. And if we show that, yeah, it's a bit hard to tell because the continuum was really low, but now these areas are basically centered on 0 because we used them to subtract the baseline. And the last thing I wanted to go over with this is, well, what if we want to do some Gaussian fitting? We can do Gauss fit. Oh, sorry, that's not how it's called. Go back. Fit Gauss, sorry. So it's fit Gauss. And then here again, it tells you what to do. So with the left button, we tell it, okay, fit that area of the spectra. Then with the center button, you can specify the center and then the width of the line. And it will tell you, okay, You can fit one Gaussian. If you wanted to fit two, you can keep clicking. And now we have two, and then when you press the right button, it will do the fitting. We can zoom into that, and we got our two Gaussians fit to the spectra. And that's some very basic data reduction analysis. Let's continue. Sorry. Any questions so far?
Could you possibly paste the file name into the chat? I think I missed it when you showed it earlier.
Oh, yes, yes, of course. Sorry. Share. There we go. Share again.
Thanks.
Were these commands listed somewhere, or like
All
are
these
they written
commands.
down?
Sorry, again.
Oh, sorry. I was asking if there's like a written out list of these commands somewhere.
Yeah, if you go into the GBT, or well, if you Google search GBTIDL, it should, or if you go into the documentation webpage and you go into a quick guide, then it will give you an overview of the most general commands, and that's probably good enough for doing some data reduction of tracking observations. If we want, if the slides will also be available, so you can check them later and follow at your own pace if you want. Okay, so that's for that. I'm just gonna skip this because it's not really well. If you go into Benjamin Winkle's article where he describes the calibration, he will mention the importance of using a vector calibration to minimize artifacts across large bandwidths, or when you have crazy standing waves. But of course, since the GBT has an offset some reflector, we don't get as you just saw it. The band pass is really flat once you do the calibration, so this is not really an issue for the GBT. And you can see that if you use a vector or a scalar calibration, the results are pretty much the same, except for a small offset. So yeah, don't worry about that. And let's jump into mapping, and that's when we, instead of just following one single position, we basically either continuously scan across a source in what's known as on-the-fly mapping, or draw a grid of points on top of our source and observe each one of those points at the same time, or you can use a more complicated pattern like a daisy in order to map your source. The specifics of the pattern and will depend again on the source you're trying to. So, as usual, discuss this with your project friends so you come up with an optimal strategy for doing this. These are some examples of the scanning patterns available. This is the daisy pattern. Um, these are on-the-fly maps in the RA and declination directions, and there are also some other crazy patterns you can use. Like, I believe this one is the spider pattern because it looks a bit like a spider web. This one is the C17 pattern because it uses 17 points across your source. Now, when you're mapping a source, you also will be flicking the noise diode on/off. But in order to derive the system temperature, you're gonna use a slightly different strategy, and that will again depend on the properties of the source, how large of an area you're mapping, and what your science goals are. But for example, if you have an object which is smaller than the area you're mapping, you might want to take, for example, the areas, and you're mapping this whole region. You might want to take, for example, these regions outside where you have emission and use this as a reference for doing the on minus off calculation. If this is not possible, there are different scan types in Astrid which will allow you to map and go and observe a reference position every so many scans. And there are multiple alternatives for doing this, but just to show that the basic idea is the same, but now because you're mapping, you might have more information to use to obtain your off position. Now, I wanted to, well, since that's going to take a while, I'm just going to jump into the GBT pipeline. So if you're doing mapping observations, the data reduction can be a bit long if you're doing it by hand in GBTIDL. So there is this thing called the GBT pipeline, which, as the name suggests, it's a pipeline for GBT observations, and this will basically take mapping scans in SDFITS format and calibrate them and output a cube or a calibrated data set depending on the options you specify. It works with most of the receivers for the GBT, particularly the ones which have noise diodes. And even though it was designed to process KFPA observations, so a multi-beam receiver with variable noise diodes, it also works with L-band data, C-band data, and some others. And this is really nice because you can really get a quick view of what your map looks like without having to spend a lot of time doing things by hand. The documentation can be found here, and the source code is also available in case you want to dig deeper into it. I'm just gonna give some of the basic options for the pipeline. So if you were to type in your fast text session from a terminal just GBT pipeline, it will spit a list of all the options and a brief explanation of each one of the flags you can use. But the ones I think are some of the basic ones are the -I flag, which tells it which SDFITS file to use, the -M flag, which allows you to specify which scans within the SDFITS file actually contain mapping observations. You can also use this ref scan option to specify, okay, use this particular scan when calibrating the data, -W to tell it which spectral window to work on if you only want to work with one at a time. You can also pass a -C option, which will basically then only create a cube with that range of channels, and this is just channel number, so no velocities or frequencies. The beam scaling parameter, which allows you to basically scale the TCAL value up or down by this amount. So like if you know that in the metadata TCAL is 1, but you measured it and it's actually 2, you can pass a beam scaling factor of 2. And that should take care of that. And you can also pass in this imaging off flag if you do not want to produce a cube at the end of it. So the way you would call it is just GBT pipeline -I, the name of your file, -M, the scans you want to map, and ref scan, the scans you want to use as reference. And let's see how this works. The real example. So go back to fastText. And go to this window. Here we go. And I already had done this, so I can do -R, GBT pipeline, like Larry just showed us. And we have GBT pipeline -I, this file here, which fortunately I cannot copy it from fastText, but I can put it in the chat in a second. And just for, let's first look at what that file contains. So we go back to our GBTIDL session. Remember, in this case, the data is old enough that it's no longer in the SDFITS area. So we use the offline command. Then we do, oops, sorry. Now I get an error message. So that's great. Yeah, it didn't work. Yeah, I don't know why that would be. Sorry about that, that's really embarrassing. But, well, basically, if we looked at a summary of this data, summarized here, we have two scans of on and off to determine the of a calibrator source to determine the temperature of the calibrator source. And then we have scans 14 to 26, where we were observing NGC 6946, the fireworks galaxy, using a map in the declination direction. You can see it was a map with 13 rows. And then the last scan is a track. Well, if you have set up the observations, you will know that this is the one you should use as a reference. So we can pass this information along to the GBT creator here. We're going to map between 14 and 26, use 27 as a reference scan, and we're only going to be interested in Windows 0 for the sake of time. And just hit return, and it will give some information about the project and the options we pass. And that was it. I mean, it calibrated the data pretty quickly, and then it imaged the data using the GBT reader, and here it tells us which commands it used. And now if I look at the contents, I see I have this cont file, and well, we'll name them source name, the scans, and the frequency of the window. And then you have cont for continuum, cube for the full spectral cube, line, which is a continuum subtracted cube, and weight, which is basically one of the weights used when averaging all the scans together. And then the pipeline also builds these two files, which is basically just the calibrated data in SDFITS format for each polarization separately. So then you can use your favorite tool to view this. In this case, let's just use DS9, which might be a bit slow. And we have an image of our galaxy. It's not very pretty, but that's because we're probably looking at a channel which is not really where we have the emission, the line emission. So we can plot the spectra, and we have this this line profile for the galaxy of interest, which is quite complicated, and you might think, oh, something went terribly wrong here. But if you actually look at the paper by DJ Pisano, where he observed this source, you see that it's not so far from what he observed, where you have these absorption features and emission next to it. And well, this is looking at the bridge between the galaxy and a companion. So it's not exactly the same position, but it basically, in this particular case, this very crazy line profile is not due to artifacts, but just because the source is really interesting. And I think I'm out of time now, so I'll stop here. And if there are any questions, yeah, I'll be happy to try to answer them.
Hey, Pedro, thanks for showing that. That complicated spectrum is just the off subtraction of the galactic H1. So it's a low redshift galaxy. So it's not, I mean, it's not absorption due to the galaxy. It's just the off, and the galactic H1 emission varies over the field. So anyway, that's what that's from. That's why it looks like that.
Thank you so much, David. Yeah. Yeah.
Thank you very much, Pedro. If there are no other questions for Pedro, now is the time of our schedule that we have everyone splitting up into their individual groups, and we will do that via breakout rooms. So I would suggest that everyone take a few-minute break. You come back at 2:45 or so to meet again with your project friends, and I will have you all split out into groups 1, 2, and 3. I will also have Pedro's talk linked from the Green Bank observing webpage. And we will let you know how to find it. All sound good?
Sounds good, Will. Thank you.
Thanks, Will.
I will split you out now.